So yeah, the recording for today's session has started. So once again, good evening to those present. My name is Jyotishwaran. I'm a PhD student from the ECE Department of Indian Institute of Technology, Roorkee, and this is the weekly discussion session for the Physics of Nanoscale Devices NPTEL course. This is session number 5. Today we shall be focusing on contents pertaining to weeks 5 and 6. So as always, any questions from the two attendees that we have today? Do you guys have any questions from the previous week assignments or lectures that you want to deal with before we start with today's discussion?
No, sir. Right now, I don't have any question.
No questions. That's good. I hope there are no questions from the other attendee as well. Yeah, so this is an interactive session in case you have not attended any of the other sessions before. You're free to speak whenever I mean, you have any questions or anything to ask or tell. And I would welcome any input from those attending this live session. Otherwise, a one-way conversation gets pretty rote and monotonous. So, all right. In that case, let us start with today's session. Just one second. All right. So, yeah. So are these slides visible?
Yes, sir.
Yeah. So uh, week 6 and also by and large week 5 essentially deals with the conduction models that we have been developing so far. So week 5 mostly primarily would have dealt with the following topics like the ballistic conduction model, where we start with the current integral expression, one which we have discussed extensively in our last week's session also. And using that, we developed the notion of modes in a ballistic channel, and the energy dependence of the mode, and so on and so forth. So these two parts were discussed last week. After that, we shall be looking at the idea of ballistic resistance and conductance. So, starting from the current expression, we shall now move into channel properties and try to define resistance slash conductance in the ballistic regime. And closely related to this concept is the idea of the Fermi window function, which, if you have started listening to the week 6 lectures, you should be familiar with now. So we shall be talking a lot about this week. And after that, we will use this model to kind of move from here to the bulk conduction model, utilizing the concept of diffusive transport, and we will try to define the concept of transit time, which we had used in, if you remember, in the definition of modes, because we use the transit time and the Heisenberg energy time uncertainty relation to define the energy broadening. And the broadening parameter was in turn combined with the density of states to give us the notion of modes. So, similarly, we shall be redefining the transit time concept for diffusive transport, and then we shall come up with this quantity known as the transmission coefficient, which is the connecting parameter between the ballistic transport model and the bulk transport model. So that is what we mean by the ballistic to bulk transition. Um, so the topics that we shall cover today are the properties of the Fermi window function. So first I shall be introducing what the Fermi window function is, and then we shall be looking at some properties of it. This will essentially be a rehash of the topics that were covered in the lectures, so I shall be quick about this. Please stop me and ask any questions if you have them. And then we shall dive into numerical calculations, because as you might have already seen, uh, so over here I am looking at week 6 and the assignments for week 6. And as you can see, we have started having numericals. So since numericals are present in the assignment, numericals will also feature in our discussions. So today I intend to spend at least half of the allotted session time in solving some numericals that should help you in understanding and solving these assignment problems, and also try to give you a flavor of what these numbers actually mean. So with that, let us begin today's session in earnest. Let me open the whiteboard. Yeah. Is the whiteboard visible? Can someone confirm?
Yes, sir.
Thank you. So first we shall start with current. So the current in a ballistic channel is given by this integral. I would like to impress upon the fact that the quantity here is the Planck constant and not the reduced Planck constant. So please remember that.
Yes, sir.
Okay. All right. So because I think last week I might have mistakenly written it down as the reduced Planck constant. So I'm clarifying it once and for all over here. So we have gamma of E times pi times d E into F2 minus F1 times, not times, dE. So this is the current integral. Oh, wait, am I missing anything here? Yeah, there is a factor of 1 by 2. Correct?
Yes, sir.
Yeah.
Sir,
Ah.
uh, during lectures, sir gave us equation with F1 minus F2. So, is there any
Oh.
change
Oh,
in
okay,
this?
okay, okay. Yes, yes, yes. Like, see, it essentially depends on what you're calling 1 and 2.
Okay.
So, yeah, F1 minus F2 is more appropriate because we always consider source to drain transfer. So, yeah, we shall maintain this over here. So, for clarity's sake, let me draw the device so that once again, oh, God. So yeah, last week was actually pretty okay because my this thing, the drawing pad that I'm using, actually worked as intended. But this week it has again started malfunctioning. So I'm essentially unable to see what I'm drawing while I'm drawing. So I'm supposed to look at the display and figure out what I'm seeing and then move accordingly here. So apologies for the shabby quality of my handwriting and the drawings. So yeah, so we have this and we have the source, which we call as region 1, correct? And then we have the drain, which is
Yes, sir.
region 2. Yes. So over here we have the channel, and all our description is for the flow of current in the channel. So this is the direction of I, which we shall also call the x-axis by convention. And what else do we have? So in general, yes, since now we have started talking about the current, do not consider this to be an exact circuit diagram. This is just a schematic representation. So I am having a, how should we have it? Plus minus, sure, why not? So I am connecting a battery to this with a voltage V. All right. You will notice that the value of V does not appear anywhere in this integral. So this is kind of the setup. We have a two terminal device. So let me clarify that also. So this is a two, oops. This is a two terminal device so far. So we are still not at the point where we are talking about transistors per se. We will get there, like, in the latter half of the course. As you might have realized, the contents we are covering is week 6, so we are at the halfway point for the course. So yeah, with that said, yeah, moving on. Now this is the expression. Now, if you may remember, it is also possible to write the above expression as what? This entire term
Me.
over here. Yes, very good. Well done. Thank you, Ichanshu. So this entire term over here can be replaced by the modes. So the modes are represented as M of E, which is an energy dependent quantity. It is a function of the energy into F1 minus F2 times dE. Now, up until this point, we are considering the current and we are discussing these terms in terms of the energy of the electrons themselves, because as mentioned before, this is a, what shall we call it? I mean, it is both semi-classical and, well, semi-classical is not the right word. This is a semi-quantum treatment. Like, quantum mechanical aspects are definitely present, as discussed in the previous week's session, because the density of states and the energy broadening, all of these are purely quantum mechanical quantities, as are the Fermi functions. So these are two ways of writing these equations. So yeah, now let us be clear and also mention that this is the ballistic current. So from now on, when I use the word ball, it is short for ballistic. So oops. So I have again, my ballistic is given by this following integral. Uh, yeah. So now let us make an assumption. So assuming source and drain are the same material. What does this imply?
So that they will have nearly same Fermi level at equilibrium.
Very good. Yes. So energy Fermi EFS is equal to EFD. So in that sense, what will happen is these two, and of course we are assuming that the temperature is constant across the device. So uh, let me just mention that. So here the entire setup is operating at a constant temperature. This is an important point, not right now, because later on in our course we shall be looking at thermoelectric effects. So at that point, of course, the source and drain operating at different temperatures will become significant. So right now we are not looking at those things. So this is also a constant temperature device. So there is a voltage V, and the only other parameter that I have to give is the temperature T. So this is the temperature. You know what? I'm just going to write. Let me write temperature. So T is temperature. Yeah. Yes. Pretty much readable. So yes. So T is crossed. Good. Huh. So first assumption is this, that the source and drain are the same material. So EF is approximately equal to EFS is approximately equal to EFD. And so therefore the quantity that we have over here is the difference between the same Fermi functions. Is that clear? Essentially what I'm saying is, because these two are same, F1 and F2 are not the same function, are similar functions. This implies F1 and F2 are similar functions. What is the difference between F1 and F2? What is the one difference between F1 and F2? So I'm writing the expression for F1. So since EFS and EFD are equal, I'm just going to call it EF upon KBT. What will F2 be?
It will be 1 upon 1 plus e raised to EF minus E
EF minus E.
upon KT.
I'm sorry, I did not get you. Hello.
Yes, sir.
Yeah, so what were you saying?
Sir, I was saying 1 upon 1 plus e raised to EF minus E by KT.
That is what will be for F2. That's what you're saying.
Yes, sir.
Uh, Look at this diagram. That contains the hint. Yes, the at equilibrium, the Fermi levels are equal. Yes, you're correct. Okay, yeah, that should also be mentioned here. So this is at, okay, let me make this whole thing smaller. You were actually very, like this previous statement that you made, that the source and drain Fermi levels will be equal at equilibrium, is a very important statement. Now, in the diagram in red that is shown over there, is the system in equilibrium now?
No, sir.
Yes. So, what will change?
So the drain Fermi level will change
Yes. So, very good. The drain Fermi level will change. So, how will the drain Fermi level change? Now, I'm asking a question about the
by
Fermi level.
QT, by QV.
Okay, so will it increase by QV or will it decrease by QV?
It will decrease by QV
Very good. Why is that?
because sir, negative terminal of battery is connected to drain.
That's not a good reason. Now the potential is a positive quantity. Let me say that V here is greater than 0. So why is the energy on that side going down? Your answer is essentially correct, but I
Because
want a more elementary, more straightforward explanation.
because sir, our charge Q is negative.
Very good. Yes. So although we are writing, whenever we are writing Q here, so that is why we are not writing it as E. Because when I write it as E, I am referring to the electronic charge. So that is always a negative quantity by definition. When I write Q, what I'm taking is the magnitude of E. So over
Yes,
here, this is a positive number. That should be remembered. So this
yes,
entire
sir.
integral is a positive number. It says that a current is moving from region 1 to region 2, which implies in which direction are the electrons moving?
From source to drain.
No, like the current is moving from source to drain.
Huh.
So which direction are the electrons moving?
In the
Oh, this
opposite,
is, yeah,
drain
in
to
the
source.
opposite direction. Yeah. So always remember that. Okay,
Yes, sir.
so essentially what is happening is the energy over here is going to become uh, like, sorry, not the energy, the Fermi level is going to be, can be written as exponential. Now I shall write it as E minus EF minus QV. Is this clear?
Yes, sir.
Yeah. So just to avoid confusion, because when the minus comes in, there'll be a plus QV. I do not want any of that confusion to be present in our discussions at least. So I shall always write it like this. Yeah, since this expression is significantly bigger. Okay, so question to the two people attending right now. Have you gone through the lectures for week 6?
Sir, I saw two lectures.
Okay, so you must be familiar with the Fermi window function. Must have
Yes, sir.
heard the name at least.
Yes, sir.
Yeah, very good. So I hope now you understand why last week since you were here last week, you'd remember that I was very happy to drop the discussion of the Fermi window function last week
Yes,
and
sir. I remember.
carry on with the modes discussion. So today we shall be dealing with the Fermi window. Now the next part is going to be pretty straightforward. So essentially what is happening is you can now view this entire quantity as a one parameter function, because over here we are integrating over E. So E in this expression should be treated as a single variable, because we are not going to vary E until we start the integration. Okay, so now this entire thing is a function of two parameters technically, the temperature and EF. But we are saying that the temperature is a constant, it is fixed across the device, so we are not changing that. But as we can see in F1 and F2, the quantity that has changed is the introduction of this in quantity QV. So I can now see the Fermi distribution function as a function of this parameter. If I change EF, the form of this function will change. If I change what to say, like T, the form will also change, but since T is a constant, we are not considering that. We are only considering the variation with respect to EF. So with that, let me open up a new board. I just wish these things opened up quicker. Yeah. So now we shall start with the Fermi window function. Yes. So now I have f of EF is given by 1 plus exponential E minus EF upon KBT. Now, what will f of EF plus delta EF be? Of course, it is going to be 1 upon 1 plus. I mean, I'm not asking these things to you guys because I assume that these are fairly simple enough. So I'm just going ahead and writing these things. Minus, okay. So whatever the value of EF is, it should be replaced entirely by E plus EF. So I'm going to write E plus delta EF. EF plus delta EF divided by KBT. Okay, so now now we can use the Taylor series expansion and essentially write this as f of EF plus uh, delta EF times del F by del or dou F by dou EF plus delta EF whole squared upon 2 factorial second partial derivative. So that is dou square F by EF squared yeah. And so on. Now, of course, here what we are doing is a first order approximation. So what does this imply? When I only take the first two terms, can someone tell me? Anyone? Hello.
Yes, sir.
So can someone tell me when I can do this? So this term, the Taylor series expansion has like infinitely many terms. When can I take only the first two terms?
Sir, when channel length is small.
Well, see, right now we are not even talking about the device. We are just talking about a function. Remember that. So over here, we are not concerned. Like as you can see, I'm not drawing the device diagram again. So
Yes,
here,
sir.
this is a property of functions. So this is, your class 11, 12 calculus. So this implies that delta EF, the amount by which we are shifting this function, is very small. Very small. All right. This is the case where we can make this
Yes, sir.
assumption. Okay. Is that
Yes,
clear?
sir.
Very good. So now that implies using the first order approximation, I can write f of EF minus f of EF plus delta EF is equal to what? It is equal to delta EF times is this clear?
Yes, sir.
So this is also like this statement is also under the first order approximation. This is very important. Delta EF has to be small. And uh, okay, so let me ask you this. What should it be small compared to? Like, what does small mean? Like, small and big are relative terms. Like, compared to one, the number 1000 is a large number, but compared to 1 million, 1000 is very small. So,
Yes.
so when I say delta EF is very small, what is it small compared to?
So compared to EF1 and EF2.
Yes, very good. So in this case, EF, because we are assuming, just one EF here.
Yes, sir.
We've stopped using EF1 and EF2 for the sake of simplicity. Okay, so this part is true. Now just set what was the thing for the previous case. Delta EF was equal to what? Minus QE. Correct?
Yes, sir.
And I know that this quantity here, f of EF, is essentially F1 and this is F2. Is that clear?
Yes, sir.
Therefore, oops, sorry, no color. Therefore, finally, we have F1 minus F2 is equal to minus QV times dou, sorry, F by dou EF. Yeah, this is the expression. But again, what is the big deal about this? I mean, I'm writing this as minus QV times. Yeah, now we've come back to the device. When I mentioned this, we are moving back to the device. Up until here, this was general calculus. So this quantity here is, let me just, for those who are not, like who have forgotten or not familiar, let me call this the Taylor series expansion. This is not technically accurate. Like if one is being very pedantic, this Taylor series expansion is not perfectly accurate. But since we are not considering that E is changing, this expression is valid. But now we are going to do some trickery. So remember this expression. So let us put this in a box. We shall bring this up. Oh, God. We shall bring this up in the next. Okay, that's as. Come on. Why can't I draw a line that is straight in my eyes? Yeah, yes, this will do. Close. So we shall come back to this expression in the next. I'm sorry, I'm kind of obsessed with these things. Yeah. So this is the Fermi window function. Yeah. So starting a new whiteboard. So Fermi window, continued. So f1 minus f2 from the previous slide is minus qb times f by dou ef. Now what is this quantity? Like, what does this function look like? We know what f looks like. So let us take the first partial derivative. So what will this be? This will be can
Minus of
uh-huh. What?
minus df by def.
No, like I want the expression of the function. So it will be this. It will be minus 1 divided by 1 plus exponential. Uh, so we do that using the chain rule. E minus EF upon KBT. Uh, the whole squared, and then we will take the derivative of this particular term. So that will come out to be exponential E minus EF upon KBT. But we are still not done because this is still like, so f was originally a function of ef, so I still have to take the derivative of this quantity here, so finally that will give me minus 1 over kbt.
kbt.
So putting all of these together, what we will essentially have is e to the power, so now let me say the following. Let me say, you know what? Just for this lecture, let me call this. No, let me not write it separately. Let me call this quantity as y. Okay, so if I'm calling this as y, then I have y divided. Oh, apologies. Yes. So what I will have is y upon kbt divided by 1 plus y whole squared. Is this clear?
Yes, sir.
Now, the trick that we will be using is that we will notice that EF and E are kind of on the same footing here. Like they are appearing in the same position. So instead of doing dou EF by dou F by dou EF, had I done dou F by dou E, what would I have gotten?
Sir, please repeat.
Like, so here I have taken the partial derivative with respect to the Fermi energy with this variable EF. Now, instead of taking the partial derivative with respect to EF, had I taken this partial derivative, E, what will change? Now, let me compactify this whole thing. I've taken too much space. I want to write more on this slide.
Sir, then we will get
Uh-huh.
minus 1 by kbt, we will get 1 by kbt.
Very good. Very good. Yes, you're correct. So, dou F by dou E is equal to minus y upon kbt divided by 1 plus y the whole square. This implies dou f by dou ef is equal to minus dou F by dou E. So this implies F1 minus F2 is equal to, making this substitution, QV into dou F by dou E. Is this clear?
Yes, sir.
So this is the function that we call the Fermi window function. Okay.
Yes, sir.
So this is the Fermi window function, and what shall we say? Like, the properties of these things have been discussed, so I'm not going to derive the properties. What I shall instead do is, since we are already nearing the halfway point of today's session, I shall briefly write the properties of the Fermi window function. But before doing that, okay, so going back, this is important. Going back one slide. This is very important. I wrote delta F is equal to minus QV. So now what condition does this place on P? Remember this, delta AF is very small. So if delta AF is minus QV, what is the condition that I place on P? Is this clear? V should also be very small. This is what is known as the low bias criteria, or the low bias condition. Is this clear?
Yes, sir.
So we have the low bias condition here. Yeah, I should have mentioned that before. Uh, so uh, why has this whole thing kind of translated to the center? No, just 1 second. Yeah, yep, much better. So this is what we are calling the Fermi window function. So the Fermi window function has been defined. So now, using the Fermi window function and the let me just split this whole thing. Now I can rewrite. Oh, sorry. Switch to blue. Should have an easier way to select the eraser on this. Yeah, so now the ballistic current eyeball can be written as what? Yes, it can be written as 2q upon h integral m of e into qv times dou f upon dou e de. Is this clear?
Yes, sir.
Now, further, we can observe that for a given condition, like at least right now, we are not doing any AC analysis of our system. We are still very much in the DC regime, because All through, I had mentioned that the voltage is being a constant. We have not varied the bias. So the bias is not only small, not only low, but it is a constant bias. So since that is the case, we can move around the constant quantities and write the following. Now this is equal to 2 q squared upon h integral m of e dou f upon dou e dE. So let me put this thing in brackets for some reason. Write this as into V. Is this part clear?
Yes, sir.
So now this implies my current I is this quantity multiplied by the bias voltage. So what is this quantity?
Sir, conductance.
Very good. Yes. So this part you must have seen in the lectures.
Yes,
So
sir.
using the relation I is equal to GV, we finally write the ballistic conductance. So also using the same subscript ball. So ballistic conductance is given by this integral m of e times the Fermi integral, not the Fermi integral, the Fermi window function dE, and on the outside we have the quantity 2q squared by h, and 2q squared by h is called the quantum of
Of conductance.
conductance. So small question, like, I mean, this has nothing to do with this course. So 2q square by h, like you can actually do the dimensional analysis and find out that it has the dimensions of conductance. Uh, what does this quantity have dimensions of? 2q by h. Just, out of curiosity, I'm asking. Okay, no matter. Like, I mean, you guys, I'm not going to waste any more time. So, this quantity it will have the dimensions of flux, actually. If you can, do the math, you'll find that the dimensions of this quantity that you have here actually matches with that of the electromagnetic flux. So while this quantity is known as the quantum of conductance, Tq by h is often referred to as the quantum of flux. It has no importance in nanoscale devices. However, if any of you guys move towards superconducting circuits, 2q by h will appear everywhere. So especially if you're dealing with the Josephson junction devices or things like that, 2q by h will be the standard quantity that you should deal with. Over here, 2q squared by h is the quantity that we are dealing with. So there is that. So now we shall look at some properties of the Fermi window function. And a comment. So this is something I want to mention. In the previous analysis, did we have any condition on the temperature?
No, sir.
Right. Like I did not say the temperature has to be low, the temperature has to be high. I did not say any of those things. So the previous analysis, what we have been doing for the last 40 minutes or so, is valid for all temperature regimes. Is that clear?
Yes, sir.
But the last part, where we kind of introduce the Fermi window function, that is valid only for low bias. I hope that you guys will remember. So yeah, going forward. So now we shall look at properties. So here I'm not going to do any derivations. I'm just going to list the things. Fermi window function. So the Fermi window function uh, will generally, the general profile, so let us say 1. So you know what, for the sake of comparison, let me also write some things about the Fermi function so that it will give you a qualitative idea. So Fermi function, I should not write it as small f. Fermi is a name of an rather exceptional physicist. So yeah, Fermi function uh, is of course f is given by, as we have written time and again, 1 plus exponential e minus ef upon kbt, and it will in general yeah, so how, what would be a good way to draw this? I'll just draw horizontal axis, that should be good. So in general, this function will have a profile that looks like this. So as e increases, so asymptotically as e tends to infinity, it can be seen that this function goes to 0. As e tends to 0, it can be seen that it has a finite positive value, the maximum of which is 1. So it will, in general, for some arbitrary temperature, it will look like this, and it will, decay off. So this is for general T temperature, non-zero temperature. The one thing that we can always be assured of is that this point where the function attains the value half, what is the x-axis value? What is the value of E here?
Sir, EF.
Yes, very good. So no matter what the temperature, so what you will notice is that as the temperature is increasing, this curve will become flatter and flatter and flatter. But no matter what happens, so let me just write the E axis over here. At E equal to EF, the Fermi function will always have a value of half. However, for let us say t equal to 0, just to differentiate it, I'm going to put the value slightly above this. It's going to be actually a constant all the way till EF. And what is that constant value? That constant value is 1. Like, do you guys know that? That at t equal to 0, the Fermi function has a value 1 until EF?
Yes, sir, we know.
Yeah. So, and after that, it goes to 0. So, after that, it is staying at 0. So, yeah. Let me say this is, yeah, 0. So, this is at t equal to, sorry, So this is at T equals 0 Kelvin. So in the same graph, I've drawn this. So what happens here? Like now here the function is kind of discontinuous. So does this same property still hold? That the value of the Fermi function at all temperatures at EF should be half. So what happened to that now?
From the graph, we can see that now that property doesn't hold.
Okay, so you guys must, I suppose you guys have some background in electrical engineering, right? Signal
Sir,
systems.
my is mechatronics engineering.
Oh, you're mechatronics. Okay, but even then, are you familiar with Fourier analysis and things like that?
Yes, sir.
So in Fourier analysis, there is a very nice property. It is that whenever a function has a discontinuity at a certain point, what we do is we replace the value of the function by the average value of those 2 points.
Yes, sir.
Okay. So what is the discontinuity here? It goes from 1 to 0 at EF.
Oh, so now we can say it is half.
Yes. Half. Yeah. So that is how we again reinforce the property that it has to be half. Okay.
Yes, sir. Yeah.
So yeah. So even at t equal to 0, the value of the Fermi function at f equal to EF is half. So sadly, I never asked this question in any of. I mean, neither me nor the other instructors and TAs asked this question in your assignments last year. So that question is not here anymore. I would have really loved to ask this question to see how many people actually catch that it is half even at t equal to 0. So yeah, so that is the reason. Okay. So all right. So these are the properties of the Fermi function. Now let us look at the properties of the Fermi window function. So this is the form of the function. So this is the form, and this is the general profile. Okay. So now what is the form of the Fermi window function? This we know. Like this we just calculated. Dou f by dou e is equal to, we wrote it as y upon kbt divided by 1 plus y the whole squared minus, because this is dou f by dou e, here y is equal to exponential e minus ef by kbt. So this is the form of the function. Okay. So now you tell me, what will the profile of this function look like? And this part must have been done in the lecture. So,
Yes, sir.
oh, yeah, okay, fine. I said I will not be asking you any questions. Apologies. Don't bother to answer. I'm going to assume that you all paid attention in the lectures and you guys know this. In case you don't know this, well, here is another opportunity. What should be observed is that at low energy values, this function is roughly a constant. So the derivative with respect to this quantity E is going to be 0. All of the changes by and large happen in this region, in and around the Fermi level. Because even after this, it can be seen that the function is roughly being a constant. Like, as it is decaying, it is a small value. So even there, I can assume it to be a small constant value. So most of the variation is happening in an interval that is surrounding the Fermi function. So in general, sorry, what we can see is that this particular uh, yeah, graph will look, apologies, since this is a graph, it has to be as neat as I can make it. There is a ruler, but yeah, I am not very familiar with how to use that. So you know what, I'm not going to use that. Uh, yes, this will do. So now, for the sake of simplicity, what I'm going to draw on the y-axis is minus dou f by dou e, because there is a minus sign already over here. Yeah. So now, for low values of energy, this function is going to be nearly 0. Okay. Now EF is somewhere over here. Let us say that. And this is the energy axis, E increasing this way. So for low energy values, let me try to straighten this patch out. Yeah. Yes. So for low values, the function is going to be, let me also use red, is going to be 0. And as I am approaching the, sorry, again, as I am approaching the Fermi level, the function's value starts decreasing. If the function's value is decreasing, what will the derivative be? Positive or negative? Can you give me a quick answer to that? If the function is
Sir,
decreasing.
please repeat the question.
If the function is decreasing, what will the value of the derivative be? Positive or negative?
Positive.
The function is decreasing. Like it is f of x plus, minus f of x plus f of, sorry, it is f of x plus delta x minus f of x divided by delta x. So as delta x is increasing, the value of f of x plus delta x is going down. So the derivative will be negative. Because of that,
Yes, sir.
minus dou f by dou e will be positive. So that's why I chose to write that over there. So it's going to be 0 for a large chunk of values, and as I'm nearing EF, it will start rising. It will start becoming more and more and more positive, and it will hit a peak value, because after this, uh, am I correct? Yes. So what is happening is the rate of change of the slope, because at very large energies, again the function is becoming a constant. So what you will notice is that it will reach a peak value, and then it will fall again, and it will go down back to 0. So it rises and it falls. So this is the rough profile for it. Let me try to pick a different color. Yeah, black is always available. So at t equal to 0, what will happen is, since it is a constant at 1, at t equal to 0, this is going to be a straight up constant line. But over here, the function is suddenly dropping to 0. So the slope will be a very large positive impulse. Well, I shouldn't use the word positive impulse. A very large positive slope followed by a very large negative slope. Okay, I apologize for my very shabby drawing. You know what? The t equal to 0 case I will draw separately. I will just leave the finite temperature case over here. Uh, yeah, so it kind of went up and down, because we also have to move on to the problems. Oh, we have a new attendee. Uh, just one second. Yeah. Welcome to the session, Rashid. We are in the middle of things, so I'm.
Thank you, sir. Sorry for delay.
That is all right. That is totally fine. The recordings will be available. please refer to the link in the chat. There is some technical issue because of which I have been unable to share the links of these videos to the NPTEL channel. That should be resolved within this week. Next week onwards, my video link should be available on the course page itself. And you should get email notifications as and when the uploads are available. For now, please find the YouTube playlist on the chat for this meeting. So that will contain video links for that right now contains the video links for all the previous sessions. Going forward, it will contain what to say like all the sessions as and when they are completed. Okay, so that is for general information. So coming back, oh God, no, times like these, I wish I had a blackboard. But yeah, I mean, that would imply that I also need a camera and a lighting setup, and that's just too much effort. So yes, so EF was somewhere over here. So what should be remembered is
The
yes,
whiteboard is not visible.
it's not visible.
Yes, sir.
Oh, okay, it just miraculously stopped sharing.
Right now it
Uh,
went.
yeah. I don't know why it stopped sharing. I never stopped sharing. Yeah, it should be visible. No, it's visible, right?
Yes, sir.
Yeah. So this is the general profile of EF. Okay. So from this we can note a bunch of properties. These should have been covered in the class. So I'm just going to list them. Uh, Dou F upon dou E. Like this is minus dou F upon dou E. Remember that. So actually the function will be the mirror image of this about the x-axis. Is symmetric about, so this is the first property about the line. Uh, what is the line? Yeah, E equal to EF. Is that clear? So this line that I've drawn here, the Fermi window function will always be symmetric about this line. Like the value on this side will match with the value on this side. Like if I move a certain distance here and a certain distance here, I will find the same value of the function. And the second point is for very large and small e, the Fermi window function dou f upon dou e is equal to 0. And thirdly, this part should have been worked out in the lecture, integral within the acceptable range. So typically whenever we write the Fermi function, as you can see, I have marked the energy as a zero energy. So it is standard practice to mark a zero energy. Okay, so this integral will always be in the limits 0 to infinity. Dou f upon dou e dE is equal to what?
1.
Very good. So these are the important properties. Now there is one more added. Uh, well, I've actually used too much space. So let me just again. Can I do that? Can I? Can I please? No, I can't. Uh, no. Yes. No. That will not do at all. Okay, so there is no way to do that. I mean, no way that I know how to do that. So I'm going to just erase and rewrite. Apologies. Uh, yes. So this integral. Let me quickly write this. Small dou f upon dou e 0 to infinity dE is equal to 1. And the third property, this is only for the uh, special case at t equal to 0. Now this is very important. At t equal to 0 Kelvin, what happens to the derivative of this discontinuous function, which I've drawn in blue here? So you can see that this is actually a step function. Like it is a unit step function. So since this is a unit step function, what will the derivative of the unit step function be? Any answers? Any suggestions? So yeah, if you guys want the explanation, please go to the. I think you'll find this somewhere in week 6, lecture 1 or 2 itself. So at t equal to 0 Kelvin, wait, the meeting is on, isn't it? Yes, the meeting is on. Can you guys hear me?
Yes, sir.
Okay, good. Uh, just 1 second. Okay, okay, I'm still there. Yeah, resharing. Yes. All right. Yeah. So at t equal to 0, dou f upon dou e is equal to minus 1 upon kBt. Uh, okay. I heard a sound. I'm still on, right? Can okay, I've lost my connectivity. Yes. Can you guys hear me?
Yes, sir.
Yeah, sorry, there was some network issue. What was the last thing you guys heard me say?
Uh, I don't
Yeah, what
remember.
was the last thing you guys heard me say?
Sir, you were asking at T equals to
T equal
0
to 0,
Kelvin.
right? Yeah, so let us continue from t equal to 0. So, yeah. So, yes. Yeah, the board is visible, correct?
Yes, sir.
Yeah, thank you. Yes, so at t equal to 0, now I'm not going through the derivations because I mean, I'm surprised. I've actually spent too much time over here on the concepts themselves. But this is important. This will actually help you solve some questions also. So the value is minus. So it is this. It is minus 1 over kBt times. Uh, just 1 second, please. Yeah, what happened? Please. No issues. Come on, your place. Yeah, drag whatever you want. Yeah, apologies for the interruption. Returning. Yes. So, you know what? I should not have written this. I'm sorry. Because at t equal to 0, that quantity goes to infinity. So, I'm sorry. Yes. So, at t equal to 0 Kelvin, this function is nothing but minus delta E minus EF. So, this is the Dirac delta function, which is defined as follows. It is infinity, like, okay, the definition that I'm writing is only for the Dirac delta function, not the negative of the Dirac delta function. So this is the part that I'm defining here. So this the function takes a value infinity when e is equal to ef, and it is 0 everywhere else, and coincidentally it also has the property integral in this case, and uh, the properties of the Dirac delta function are like there are several, but as far as the integrals that we are dealing with right here, I'm not going into all the properties of the Dirac delta function. Integral 0 to infinity delta E minus EF, as long as my EF is a positive number, is always equal to 1. So the same property that we wrote for the Fermi window function is also satisfied over here. Okay. So, okay, yeah. So this quantity is minus 1. I'm sorry, because this is minus dou f by dou e. Am I audible? Can you guys confirm?
Yes, sir.
Yeah, good. Okay. Yeah, I'm sorry, I'm late in asking that question also. So yes, we are done with this slide. And okay, so before I move on from this, for week 6, solving many of your questions, you will need an understanding of the. Oh, you're not the right slide. Uh, yes, this is the one. Yeah, so you'll need an understanding of what modes are, what the quantum of conductance is that has been introduced, and the properties of the Fermi window function, which has also been covered. So, with this, let us spend the last half hour doing some numerical questions. That will be somewhat similar to your assignment questions, but they are not exactly your assignment questions. So again, do not expect that. Uh, so okay, so now some sample problems. So now I'd like to hear from you guys as well. Okay, so problem one is okay. First, I know that the ballistic conductance or the ballistic quantum of conductance essentially. So, oh, sorry, wrong color. I have to erase that again. Yes. So the quantum of conductance is what is it given by? Someone? Anyone? Please. What is the expression for the quantum of conductance?
H.
Huh?
Sorry, it's a quantum of conductance. But
Yes.
2q square by h only.
Very good. 2q squared upon the Planck constant. Q is the magnitude of the electronic charge. So what is the quantum of resistance?
H by 2q square.
Yes. So can you tell me what that value is? Like this must have been calculated in the lecture.
No, sir. Means I have not seen so far.
Okay. Okay. No worries. So we can substitute the values right here, and we can see that. Yeah. So essentially, is equal to what? H over 2 q squared. That is equal to 6.62 into 10 to the power minus 34, and ignoring the units as they are not required, we just want the numerical value. because we know that this has units of conductance, the reciprocal has of that has to have the units of resistance. Divided by 2 into 1.609 into 10 to the power minus 19 squared. So before we do any calculations, can you tell me what will be the order of this? Like this is going to be in ohms. So is this going to be in milliohms, kiloohms, megaohms, microohms? What is the value going to be? Just quickly by glancing at it. You can see that in the denominator we have 10 to the power minus 38 and in the numerator we have 10 to the power minus 34. So that gives us a quantity that has a value of approximately 10 to the power 4. So this is going to be in the kilo ohm region. Okay. So the exact numerical value will come out to be 12.906 kilo ohms, or rather 1.29 into 10 to the power 4 ohms. So this is important. This is important for you to understand that even though we are talking about, a ballistic channel and transmission of electron from the source to drain without any collision or scattering, the actual value of the resistance for that channel is still a non-trivially large quantity, and this quantity is actually pretty comparable to the bulk devices that we know. Channel resistance is typically to the order of kilo ohms. If you can go back and look at certain JFETs or BJTs, you'll find that these resistance values that we are showing here are pretty much par for the course. They are in the range that we are used to. So even though we are talking about ballistic conductance, where we have a collision-free transmission of the electron through the channel, there is still a non-trivially large resistance. Okay, so this is the first part you have to remember. This is a constant that is always good to remember. The reciprocal of this will give you the value of the quantum of conductance. Go ahead and do that on your own free time. So the second question, again, these are brief questions that should kind of give you a pointer. So if this is the case, then in general, what is the ballistic conductance expression? I've told you that h upon 2q squared is this. So now what is the expression for ballistic conductance based on what we have learned so far? We can write that as 1 upon 12.9 into 10 to the power 3 into integral m of e times dou f upon dou e dE. Is this correct?
Yes, sir.
Okay. So based on our properties, we know this is the ballistic conductance. Okay. Now, at t equal to 0, what is the ballistic conductance? This is the question. What is G ballistic? Sorry. What is G ballistic? I want one of you to quickly answer this question. So what happens to the Fermi window function at t equal to 0? We just saw that, like in the previous slide. At t equal to 0, what happens to this Fermi window function? What does this function change into? Do you want me to open the previous slide?
Yes, sir.
Okay, let me open the previous slide. Again, like if you have any, like I'm not only asking these questions to hear the answers from you. In case you don't know the answer, tell me you don't know the answer. It is fine. As I've mentioned before, and I'll continue to mention, you're not being evaluated for participating in these sessions. Like participation A is completely voluntary, and whatever you see here will in no way affect your grades. Like your grades are all calculated by an automated system. So, so feel free to speak here. At t equal to 0, what happens to this Fermi window function? It becomes the Dirac delta function.
Yes, sir.
Okay, so now coming back to our question. Yes, why is this thing auto centering on its own for whatever reason? Yes, so yes, so now at t equal to 0, the ballistic conductance can be written as is equal to integral me into delta E minus EF dE. So this is also a property of the Dirac delta function. This will be covered in your lectures. I am not again going through the proof for that. It will A take time, B not necessary. Whenever I have an integral, and of course this region of integration is, this is like over all possible values of E, be it from 0 to infinity or from minus infinity to infinity. This integral takes into consideration all possible values of E. So this integration definitely contains the value of EF also. In that case, the property of the Dirac delta function tells me that the answer to this is m of EF. Is this clear?
Yes, sir.
Okay. So at t equal to 0 Kelvin, the ballistic conductance, oh sorry, 2q square upon h, I missed the constant. Yes. So now since we already know the value, that is 12.9 into 10 to the power 3. So it is number of modes, not minus 3. 3. My God. Yeah. Yes. So the number of modes divided by this quantity gives me the value of the conductance. So this is the expression. So you can, if you can find out the number of modes at EF, then you know what the channel conductance is at T equal to 0 Kelvin. The reciprocal of this quantity, therefore, at T equal to 0 Kelvin, the ballistic resistance is equal to 12.9 into 10 to the power 3 divided by MEF. So if I tell you, so this question is particularly to Ichanshu because he was here last week. How many modes did we calculate for the hypothetical channel that we considered?
Sir, I don't remember.
It came out to around 25. Okay,
Okay, sir.
okay, so it came out to around 25. So if MEF is around 25, let us say at 0 Kelvin the number of modes is 25, then what will be the value of the resistance?
Sir, zero point 0.5 kilo ohms.
Yeah, approximately. Very good. So it will be zero point 0.5 kilo ohms or 500 ohms. Correct?
Yes, sir.
Yeah. So that is how these calculations will go. Now, as a refresher, so yeah, since I said there will be numerical examples, now we shall consider certain particular examples with a 2D channel. And why aren't you opening? Please give me a. Have I run out of memory or something? No, everything seems to be okay. So yeah, let me just quickly close and restart this. Uh, Yes. So, yeah, the board is open. Yes. So now the following problems that we shall consider are all for A to D ballistic channel. So, starting, we are saying consider A to D ballistic channel. What should we have the length to be? Um, so what are the dimensions of the channel? Let us say the channel has dimensions of say 15 nanometer by 10 nanometer. So this is the channel. This is the x direction, which implies the current is flowing this way. So 15 nanometer is the channel length. And let us say EF is equal to, how much shall we say EF is equal to? Let us say the Fermi energy is equal to 5 electron volts. Okay. So first, can you calculate? Okay, so I would, Ichanshu, I would appreciate it if you can, like chime in here, because the other two attendees who were present were not here last week, so they will not have an idea of what we are talking. So if you can walk through along with me as to what we are doing here, it would be nice. So first, can we calculate M of EF? Is it possible?
Yes, sir.
Okay, so how do we do that? So for this channel, I know L equal to 15 nanometers and W is equal to 10 nanometers. So yeah, so tell me, like, give me, you don't have to give me the value of the
Huh.
thing. Tell me how to do it. I will do the mathematics.
Uh, Sir, for ballistic channel, ME will
Yes,
be uh, gamma E into D into pi by 2.
yes, yes. But
Uh,
for a 2D channel, we got a special result. It will
uh,
be, do you remember? It will be W divided by lambda B by 2. Correct?
yes, sir.
Yes. So this is important. This should have been covered in your like week 5 content itself.
Yes,
So
sir,
that is
it
a
is covered.
concept, yes, you have to use. So this is channel width divided by lambda EF. In this case, since we are talking about a particular energy, we are talking about the de Broglie wavelength corresponding to the Fermi level. So that divided by 2. So essentially we are asking how many half wavelengths will fit into this. So first and foremost, we'll have to calculate lambda EF. So how do we calculate lambda EF? Assume also assume m star is equal to m. Like, I'm not worried about any propriety. Apologies. Any propriety in that regard. So yeah. So mass of the electron is the, what is it, like, effective mass is the rest mass of the electron. So what? How do we calculate this quantity lambda EF? Just tell me the formula. I will do the calculations.
Sir, lambda EF 2 pi by k.
Yes, it is 2 pi by k. Wonderful. How do I find k then? So lambda EF is also equal to h by p. Remember from the de Broglie
Yes, sir.
relation. So I know the energy is 5 electron volt. Since I know the electron energy is 5 electron, that's why I gave the value of the mass here. That was a hint. So you can write the momentum as square root of 2 me. So this is h divided by square root of 2 into m into e. Is that clear?
Oh, yes, sir.
Ah, okay. So yeah, so let me do that. You guys can also follow along with me, no issues. Uh, so that comes out to be approximately 5.5 into 10 to the power minus 10 meters. Okay, which is equal to 0.55 nanometers. So tell me this, if this is half a nanometer and if I have a channel length of 15 nanometers, can I still consider ballistic transport? Any comments? Now all three of you can comment. Okay, I think.
Sir, am I audible?
Yes, yes, yes. I
Sir.
think I got cut out. Yeah.
No, I got cut off.
Oh, okay. You got cut out. Okay. So, yeah, go ahead. My question was, this is the calculated value of the wavelength, and the channel length is 15 nanometers. So, is ballistic transport still valid? Is the analysis of ballistic transport still valid?
Yes, sir.
Good. So what we will see is this is around 30 times the wavelength.
Huh.
So that is
Huh.
still comparable. Like it's not too large. So typically when we consider too large a value of channel length, we'll go to at least 100 times. Okay, as a practice.
Okay, sir.
Okay, so this is less than 100. So ballistic analysis still holds. So now that is zero point 0.5, so 0.55, what is it, like nanometers. Now tell me what will be MEF. I've given you lambda F, you know what W is. Now this part I would like you guys to do. So substitute and give me the answer for the number of movements.
Sir, 36.36.
Yes, so you know approximately
36.
36. So we have 36 modes at the Fermi level. Okay,
Yes, sir.
so now tell me what will be the ballistic resistance at T equal to 0 Kelvin.
Sir, 2.8 kilo ohms.
2.8. Are you sure? How did you do it? Can you tell me? Tell me what the formula is. like tell me whatever calculation you used. Again, it doesn't have to be right.
Hello, sir.
Yeah.
Am I audible?
Yes, you're audible. Go ahead.
Sir, I did ME by 12 point. That formula that you gave,
Okay. So ME by 12 point.
something of this.
Yes. So what is that? Is that the conductance or the resistance? Yeah.
Sir,
Take a
it
look.
is conductance.
Yeah. So what you're supposed to do is 12.9 divided by ME.
Uh,
So yes. So if you
so
do
for now,
that,
it is point
yeah.
0.5.
Huh?
So I calculated conductance to be 2 kilo ohms. So now it will resistance will be zero point 0.5 kilo. Sorry, milliohms.
Uh, Again, you made a small mistake there. It is 36 divided by, like, it would not have been kilo ohms. It would have been not kilo Siemens. It would have been millisiemens, the conductance. Because in the denominator, you have 12.9 into 10 to the power 3.
Yes, sir. Yes, sir.
So over here, it is equal to, why am I auto centering on my own? Yeah, so this is equal to 12.9 into 10 to the power 3 divided by 36. So this quantity will come out to be approximately 0.355 kilo ohms or 355 ohms. Okay. Hello. Someone? Anyone?
Yes, sir.
Please. Yeah. Okay. You got this. Good. So this is one kind of problem that we can solve. Some of your assignment problems will look like this. Remember, whenever we go to t equal to 0, for ballistic case, you have to calculate MEF. That is all. And then you divide it by this quantity, which is a constant. 12.9 into 10 to the power 3 is the quantum of resistance. So that divided by MEF will be the resistance. The reciprocal of that quantity will be your conductance. Okay.
Yes,
So
sir.
this is problem 3 technically. Uh, oh, sorry. God. I do dearly hope these things would actually open rather quickly. Yes. So yeah, now yes, let us do something for the last problem. Okay, so today because of time constraints and also because we have not discussed it, I shall not be going too much into the um, diffusive transport. However, the logic behind diffusive transport is essentially the same. Oh, or don't worry. I mean, we still have around 10 minutes left. I will also do one example for diffusive transport. That should give you kind of a hint. So now, more importantly, let me say that, so this in this question, I have a 2D channel again with surface charge density NS equal to, say, uh, 2 into 10 to the power 16 electrons per centimeter squared. Okay. So I want you to tell me what EF is. Can you, do you guys know how to do this? Anyone?
No, sir.
Okay. So I will tell you this part. Like, it's there in the lectures. So once you go through the lectures, you will understand it. But right now, I'll just tell you how to do it. So consider the case that T equal to 0. Okay, so consider T equal to 0. You know what, I'm going to write the solution part for this in red. So consider T equal to 0 Kelvin. So tell me this, at T equal to 0 Kelvin, what will be the highest energy of one of these electrons? What is the highest energy at 0 Kelvin for the electrons in this 2D channel?
Sir,
Yeah.
it will be equal to the Fermi level.
Yes, very good. The highest energy, yes, you're right. Highest energy is equal to EF. You know, that's by definition. If you remember our Fermi function plot, at EF, the thing drops to 0, which implies the probability of finding an electron with E greater than EF is 0. The probability of finding an
Yes.
electron until E equal to EF is 1. So you will definitely have an electron having that energy. So the highest energy of this system is EF. So since that is the case, now I have to find out how many such uh, how many such uh, like not how many. Now I know that there are 2 into 10 to the power 16 electrons per centimeter cube. Okay, that is the density. Now can you tell me something more? Okay, more important question. How many dimensions will the K space of this system have? One dimension, two dimension, three dimension?
So two dimension.
Very good. Yeah, it's a 2D channel. So I have Kx and Ky. Okay. So what is the highest value of energy? That is Kf. Correct?
Yes, sir.
So what I will have is a circle of radius Kf. Okay. And more importantly, inside this K space, now remember what we discussed way back in our very first week. Yeah, now I can say that you can go back and watch the videos. The K space variables essentially tell me what are all the available electronic energy states. So for each of these available electronic energy states, I can have two electrons. So 2 into pi kf squared, that is the area of this entire circle, divided by what is the area of one state, like one, what is the smallest, like if you remember the density of states calculation, what is the smallest value of the k space interval? Do you remember?
Decay.
Yes, yes. So what, like delta k, in this case k, kx and ky are discrete, so what is the smallest value? Now it's a 2D channel of this form. It is of length L and width W. So you will find out that the smallest, like the essentially dkx, dky, for this case, like if you go back and look at your density of states derivations, you'll find dkx, dky is equal to 2 pi the whole squared divided by, or rather dkx should not be the right way to write it. I should write it as delta kx, delta ky. Delta kx, delta ky can be written as like 2 pi by L into 2 pi by W. Do you guys remember something like this? Hello, am I still audible?
Hello. Sir,
Yeah,
it was pi by Lx and pi by Ly.
pi by Lx or 2 pi?
Sir, pi by Lx means
Really?
I have the notes. I was making written notes.
Oh, okay, okay. You are making
Just
written
review.
notes. Okay. Yeah, so it will come out to be pi by Lx, but that, if you remember, is for the what do you call that? Particle in a box normalization, correct?
हाँ sir.
We took particle in a box as an example. So in
हाँ.
this case, what you are supposed to do is not take the particle in the box, you are supposed to take a free particle example. So in that case, it will come out to be 2 pi by Lx and 2 pi by Ly. Yeah, since you said Lx
Okay.
and Ly, that's actually a better uh, notation. I shall also use that. Um, so, so in that case, it will come out to be 2 pi by Lx and 2 pi by Ly. Okay.
Okay sir.
So again, this part is covered in your lectures. I'm just quickly rushing through it. Okay, divided by Ly. So this quantity is 2 pi the whole squared divided by Lx Ly. So that is what I shall be dividing this thing by. Do you understand? Like this is the entire area, and for each state there are two electrons. So
Yes sir.
now this is 2 pi the whole squared into Lx Ly, that is equal to the number of electrons, total number of electrons n. Now I don't know what the total number of electrons n is. However, I've been given the electron concentration. And what is that? That is n divided by Lx Ly. Sorry, I wrote Lx. Is that clear?
Yes sir.
So n divided by Lx Ly is that quantity. So 2 times pi kf squared divided by 2 pi squared, 2 pi the whole squared, is equal to n divided by Lx Ly, which is equal to ns. Therefore, kf squared is equal to, like cancelling all the quantities out, uh, yeah, 2 pi ns, which implies kf is equal to 2 pi ns whole power half. Wait, wait a second. Yeah, this is fine. Okay, 2 pi ns whole power half. So now using this, and again, I should have mentioned what the effective mass was. If I said m star is equal to me, then you can find out EF is equal to what? It is h bar square kf squared divided by 2m star. Is that clear?
Yes sir.
So once you find EF, again you can find MEF. Once you find MEF at t equal to 0, you can find the resistance of this channel also.
Yes sir.
So so now you understand that how these quantities connect to like macroscopic measured values? Like essentially, if I give you a 2D channel and if I tell you what the charge carrier density in that channel is, then you can guess what the zero temperature resistance of that channel will be. Zero temperature ballistic resistance of that channel will be using this method. And you have a question in your assignment that requires you to do this. So I have given you the sketch of this. It will be done in detail in your what to say lectures. So, I think we can stop here because, we have reached our 2 hour time limit. Uh, Moving from here to diffusive transport, yes, there is a little bit of derivations. I suggest that you follow it from the lectures. But remember, ultimately, it all comes down to writing the integral, identifying the modes, and multiplying it by the Fermi window function. And whenever you are asked to evaluate or calculate a quantity at t equal to 0 Kelvin, which is what you will in general be asked, like in your assignment or your exam questions, most of your calculations will be at 0 Kelvin. Okay, at least in this portion of the course. Remember that at 0 Kelvin, the Fermi window function becomes a Dirac delta function. And because of that, this integral becomes a constant quantity. And I just have to calculate the number of modes at the Fermi energy. I just need to calculate MEF. Once I've calculated MEF, I can use that to obtain the conductance and the resistance values. Is that clear?
Yes, sir.
Okay, so that what we have discussed and covered so far should enable you to answer, at least 6 or 7 questions from the week 6 assignment. I suggest you go through the lectures in lectures for the diffusive part. If you have any questions there, please post them on the discussion forum. I do see the questions there. I respond to them occasionally. So, I mean, there is another TA also who responds to most of them. So you can post your questions there and they will be answered. And for the other stuff, you can, use what we have discussed here. These videos will be uploaded on the YouTube channel and they will be available for all attendees of this course. So, yeah, with that, we come to the end of this week's discussion session. I once again thank you for staying online and joining me for this discussion session. I hope the contents of our discussions was of some interest and benefit to you. So we will meet again same time next week. So yeah,
Excuse me,
thank
sir.
you and yeah, yes,
Sir, out of curiosity, I was
yeah. Please,
having a question
please, please go
that,
ahead.
huh, that we use the quantum approach for means calculating the quantities like conductance and all in the ballistic case.
Yes.
But as I can see further, we will
Uh-huh.
use the same approach to calculate it in the bulk
Yes.
transfer.
Yes.
So I was thinking that we already know means these quantities in bulk transport case by our classical mechanics. So what is the
Yes.
use of
Okay.
means making the approach from the quantum side?
Okay. So making the approach from the quantum side, you can see like so far we have introduced some new concepts also. You can see that the at least the ballistic transport analysis. It's not a purely quantum analysis. The ballistic analysis that we are doing here, you see that it has certain curious properties. Like we talk about the transit time, we talk about the velocity, like the average positive velocity and things like that. Correct?
Yes, sir.
So in general, when you do the macroscopic analysis for bulk devices, you don't talk about these things. You don't talk about transit time or things like that. You talk about a relaxation time, sure, but you don't treat the motion of every electron individually. There is certainly no concept of modes. Correct?
Huh. Yes, sir.
Now, when we do the transition from ballistic to diffusive transport, we will see what roles the modes play. Do the modes vanish when I have a very long channel? They shouldn't, right?
Huh. They shouldn't.
So what happens to the modes there? That will give you a better way of visualizing and understanding because how do I say this? So yeah, what I'm about to say might sound weird, but by and large that statement has validity. You see a macroscopic device. Okay,
Hmm.
you can see a BJT, even like a lump circuit element that you're using on breadboards. So that thing is a few millimeters
Hmm.
across. But even in
Huh.
that large a device, the electron is still a microscopic particle.
Yes, sir.
The behavior of the electron is always quantum mechanical. The
Okay.
quantum and classical analysis that we talk about is for our understanding. At a certain energy level, at certain time scales, at certain size, like geometric scales, treating them as classical particles will give us approximately correct answers.
Hmm.
But at all scales, an electron is a quantum mechanical particle because that is
Yes,
the
sir.
fundamental nature of the electron. So, this derivation, where you will see certain new factors appearing, will connect the classical and the quantum regimes, so to speak. I mean, I should not say the quantum regimes, the ballistic and the diffusive regimes. So, it will
Hmm.
connect that. You can see how ballistic transport transforms into diffusive transport. So that should
Yes,
give
sir.
you a greater degree of appreciation, and you will also understand what changes. Like if I make the channel say 100 times longer or 1,000 times longer, how much will my resistance change by? Like
Hmm.
conventional knowledge will say that okay, if my ballistic channel had a certain amount of resistance, then placing 100 of them in series should increase the resistance 100 times. Correct?
Yes, sir.
Right, that would be my logic. Correct? Does it
Yes,
increase
sir.
by 100 times? Or does it
Hmm.
increase by something more? Does it increase by something less?
Hmm.
When does it increase by 100 times? You will see the answers to all of this has been discussed in week 6 in a way. So that is the idea here.
Okay, sir.
Okay, I hope that answers your question to a certain
Yes,
extent.
sir.
All right. So yeah, thank you, Vichanshu. I mean, I see that Rashid had left because I had declared the session closed. So no offense
Yes,
to
sir.
him. So yeah, with that, since the question that you asked was interesting, I thought I will answer it in the recorded part of the session itself, so that other people seeing this can also benefit from it.
Yes, sir.
So yeah, thank you for your questions. So we'll meet
Thank you, sir.
again same time next week. All right.
Yes, sir.
So I am ending this meeting. So bye bye.
Yes, sir.